Hello and welcome to a video about momentum. This is for Unit P2 and for GCSE Science. Now, to work out the momentum of an object, we have to have two measurements for it, and those two measurements are the mass and the velocity. So the momentum of any object depends on its mass and its velocity. So how do we work it out? Well, we just use this formula, but before we do an example, I just want you to know the symbols for these quantities. And for momentum, rather unhelpful, but it's a small p, a lowercase p. For mass, it's a small m and a small v for velocity. So these are the symbols, but you also need to know the units. So the units for mass are kg, velocity is meters per second, and therefore momentum is kg meters per second. You will be given this formula in the exam, you will be given these symbols in the exam, you won't be given the unit, so it's important that you remember what the units are. So let's do a couple of quick examples before we get on to some more slightly challenging questions. So for this trolley here, how do we work out momentum? Very simple, we need the mass and the velocity. I've given an example of 2 for each. So if we're working out the momentum for this object here, it will simply be a case of 2 times 2, and the velocity, not the velocity, the momentum therefore would be 4 kgms. We can also change the momentum, and all we'd need to do is change the mass. So in this case I have increased the mass to 4, and if you're thinking ahead a little bit, you'll just realize that this is actually just, I've doubled the mass, kept the velocity the same, so the momentum is now 8 kgms. I could also change the momentum by not changing the mass, but by changing the velocity. So I've kept the mass the same here, I've doubled the velocity, and again it works out as 8 kg meters, keep doing that too much, equals 8 kg meters per second. Okay, so that's what momentum is. That's a couple of very simple examples. We're now going to get into a couple of more involved answers and look at this idea of conservation of momentum. So the conservation of momentum, this is something that you do need to know about. The conservation of momentum says that the total momentum before an event is equal to the total momentum after the event, and by event we mean either a collision or an explosion. So we're going to look at these two scenarios now. So the example I'm giving here is a car moving at 20 meters per second. Let's give it a mass of 1000 kg, and that car bumps into another car which has exactly the same mass, so let's call that also 1000 kg, but this car is actually not moving. So if it's not moving, its velocity is 0 meters per second. So the two cars then collide, so the first car at the back there collides into the second car, and they then move off together. Okay, so they stick together and they move off as one together. How can we work out the velocity of this moving pair of cars? Well, in one way you could just look at this and say, well, if the two masses are the same, one's going 20 meters per second and one's going 0, you'd expect the second car to have a slowing down effect and the first car to have a speeding up effect of the two joined together. And if you do, you would actually, if you did work that out, you'd actually meet somewhere in the middle. It would be 10 meters per second. That would be the velocity of the two joined together because the masses are the same. We could work this out mathematically because we don't always get scenarios where the masses are the same. So we could work it out using our formula, and we could just say, well, the total momentum before the event is equal to the total momentum after. So what is it before? The momentum before is the individual momentum of the two cars. So sometimes they label this as P1 and P2. So the momentum of the two cars together is, let's do the first one first, so it'd be 1000 times 20 equals 20,000 kgms. The momentum for the second car is again 1000, but this time it's times 0 equals 0 kgms. And remember what the total momentum, so add those two together, we stay with 20,000. So that's the momentum before the event. What's the momentum after the event? Well, this law says it's got to be the same. So that means the momentum of these two cars together is going to be 20,000 kg ms. Now, how would we work out the velocity? Well, I know we've got it here, but if we didn't have it here, how would we work it out? Well, again, we could use the formula momentum equals mass times velocity, and we know the momentum is 20,000, so it's 20,000 equals, right, what's the combined mass of these two? Well, we haven't written it here, but we do know from the first part of the question that both have a mass of 1000 kg, so together it's 2000 times velocity. And to work out the velocity here, it's a simple case of rearranging the formula, and if you're quite good at math, you'll realize that it's 20,000 divided by 2000, and that gives us an answer of 10 meters per second. This corresponds with what we worked out in the previous way. Okay, so the velocity after using this idea of conservation of momentum is 10 meters per second. Okay, now this could get a little bit more tricky if you have a scenario where the two masses aren't the same, but however you work it out in exactly the same way. So this is just an example of a question. It says here, a movie scene involves a collision between a truck and a car. Calculate the velocity of the joined car and truck after the collision using the given data. So we've got a whole bunch of data here. We want to work out the velocity of the car and the truck as they move off after they have collided. So we use the same scenario, same way. So the total, it might be useful to have our law here. Total momentum before is equal to the momentum after the event. So what is it before? Well, we calculate the momentum of the truck, we'll call it P1, and the car P2, and we'll add those two together. So for the truck, it's 5,000 times 20 equals 100,000, and for the car, it's 1,000 times 10 equals 10,000, and the total momentum would simply be a case of adding those two together. So we have 110,000 kg m/s. Okay, so that gives us the total momentum before, and in fact, based on this law, it's the total momentum after as well. So the momentum of these two joined together afterwards is going to be the same as 110,000 kg ms. Now, if you want to work out the velocity of this moving structure, how do we do that? Well, again, we just use our original formula. Momentum equals mass times velocity. We know the momentum, we know the mass, we don't know the velocity. So let's plug in the numbers. The momentum is 110,000 equals the mass. Now it's not written here, but we know the mass before, it's 5,000 and 1,000. So add those two together for the truck and the car joined together, that is 6,000 times the velocity, which we don't know yet. Again, if we rearrange the formula, we get 110,000 divided by 6,000, and that works out to be 18.3 meters per second. So the velocity of the truck and the car joined together is 18.3 meters per second. And we can do a quick check here, because we can say that, well, the truck was traveling at 20 meters per second, the car at 10. The truck has a much bigger mass, so you might think it might have a bigger effect on the joint, or the two vehicles join. In actual fact, it does. It makes the car go a lot faster, or it actually moves nearer to the momentum of the truck as it was originally, rather than the car as it was originally. Okay, so that number seems to make sense. Okay, so you've got two examples there of how you can use this idea of the conservation of momentum using the formula. I just want to quickly go through one last example, and that's the idea of an explosion. The specification says that you might be looking at explosions and or collisions. So how does it work in the scenario of an explosion? And the example I've taken is a cannon which is firing a cannonball. Now, how do we work out the velocity of the cannon in this scenario? The cannon is going to fire back or shoot back that way, and we call that recoil. The cannonball is going to shoot off that way. So how do we work it out in this scenario? Well, again, the conservation of momentum is important, and if we look at the momentum before this explosion has happened, well, none of them are going to be moving. So even if you work out the mass, 200 plus 0.5 times the velocity is 0, so the momentum before equals 0. Okay, so let's see if we can work out what's going on. After the explosion, well, we've got to add the two momentums together. So for the momentum of the ball, it's 80 times 0.5, which will be 40. And over here, we've got 200 times v equals 40. So the answer is 200 times v equals 40. And if you do the calculation, simple case of 40 over 200, which is 0.2 meters per second. Okay, so the velocity of the cannon is going to be 0.2 meters per second. But then how does that relate to the momentum before and after being 0? Now, an important thing to remember here is because the cannon is moving in the opposite direction to the ball, we have to give this a minus. Okay, because as you know, velocity has direction, and the way we show the direction in this case is we give the cannon a minus 2 meters per second because it's going in the opposite direction, and the velocity of the ball has a plus. And if we were to make sure that our law of conservation of momentum works, then we have to have this minus number here, because when we work out the two momentums, they must become 0. So let's do that for you quickly. So I've just written it out here for you to avoid you having to watch me write it. But for the cannon, if we work out the momentum for the cannon, it's 200 times 0.2, which is minus 40. Important that you have the minus there. And for the ball, it's 40 plus 40, and we said before the momentum was 0, and that must add up to the momentum afterwards as well. So if you take minus 40, add 40, the total momentum is 0 of the system. That's very important. So the one last thing I'll say here is that remember, velocity has direction, and because velocity has direction, so does momentum, and that's useful in calculating quantities in explosions. So quite a long video. Thanks for bearing with me if you got this far, and thanks for watching.